Okay, so in this session, we'll discuss a bit more about FFT, fast Fourier transform. But before that, remember the problem I gave in the previous session about the expected area of the convex hull? Okay, so it relies on linearity of expectation. The details of the solution I described are not enough. For example, we only tackled about determining the points on one side and then finding the probability that they're removed. Now, the problem with that, you also need to determine the probability that these 2 points are visible in the first place. Okay? Not just the probability that all the points in one side are not visible. You have to also determine the probability that these points are visible. Okay? Another thing, if there are collinear points, then you have to be careful about this case. I think one way you can fix the solution is don't consider lines that contain some point inside them. Okay, so you don't double count area contribution. What?
What is visibility of line?
What do you mean visibility?
You said this line should be visible. Can you give an example? Like what does it mean?
I said only consider lines which don't contain some point in between them. That's it. I don't think I said something about divisibility. If I did, sorry about that. Okay? So I think one way to fix that solution is when you find collinear points, only consider the chunks that don't contain points inside it. Okay? So that's it. And now let's discuss FFT. I hope you know what at least the basics of FFT is. So FFT, it's a fast way of multiplying two polynomials. That's the most important application of that in algorithmics. It's into multiplying two polynomials. Okay? So how does it multiply two polynomials? So let's say you have a polynomial of degree n. So remember that if you have some polynomial and it's of degree n, then you can uniquely identify this polynomial with exactly n plus 1 points. Okay? At least n plus 1 points that, let's say you plot this function, this graph, you'll get some curve. If you select n plus 1 points, where this curve passes, then those points uniquely determine this polynomial. Okay? And there's a simple proof of that, which is, let's say you have two polynomials, p of x and then g of x, which have a degree of less than or equal to n. But they pass through n plus 1 identical points. Then if we take this difference, you'll get some polynomial which has at least n plus 1 zeros. Because if you subtract these polynomials and they pass at the same point, then if this one will, the excess of those points will be the zeros of this polynomial. Okay, so there are at least n plus 1 zeros, but the degree is at most n. Therefore, this has to be the zero polynomial, because otherwise there has to be at most n zeros. That's why p and g are the same. Hence, there's a unique polynomial that passes through at n plus 1 given points. So how do we use that observation? When you have two polynomials and you want to multiply or add them or anything, of course, multiplying them naively takes n squared time, or if you use Karasuba multiplication, you'll get something faster. But if P and Q are represented using n plus 1 points, and let's say they're of degree n each, okay, let's say they're of degree n each. So their product must be of degree 2n, right? So if you take 2n plus 1 points where this curve passes and this curve passes, and then you take them, and let's say you assume you have taken them with the same x's. Okay, so let's say you have something like this, and then you compute p for all of those x's, and then q as well. Now this polynomial evaluates to the product of these values for each of those x's. And there are 2n plus 1 points here. Therefore, those values uniquely determine the product. Okay? But multiplying pairwise is very fast. That's why if you represent polynomials in this form, multiplication, addition, etc., it's easy. The only thing that matters is, or the only thing that's important is, the number of points must be enough. Okay, so you have to know the degree of the final output. And you have to take at least that many x's. Otherwise, you won't get a unique polynomial. Okay? The only problem in this case is you want to convert given from the coefficient form into this form, evaluating to multiple points. Okay? And in general, that's not an easy problem. But if we select the x's in a very particular way, then the evaluation can be done quickly. And this is a trick that FFT does. The choice is, let's say you want to evaluate some polynomial on up to, let's say, 2 raised to k. Let's just say you want to evaluate it at n points. And let's say n is greater than the degree of p. Okay? FFT selects the x's to be the nth roots of unity. Okay? What's an nth root of unity? It's a number x such that if you raise it to 1, you'll get 1. If you raise it to n, you'll get 1. Okay? And this x is not necessarily a real number. It can be complex. Okay? But if x is complex, then by the fundamental theorem of algebra, this has n roots. Okay? So, and that's precisely where you evaluate this polynomial. Okay? So we can write the nth roots of unity this way for k from 0 to n minus 1. This is the set of nth roots of unity. Okay, why? Because if you raise it to n, you'll get something like this, which we know to be, by De Moivre's formula, something like this. But this is 1, this is 0. Therefore, this is an nth root of unity. And all FFT does is evaluate a polynomial on these points. And usually, we select n to be a power of 2. Okay, so if your degree is not a power of 2, then just take the power of 2 that's larger than the degree. Because there's a neat way to express the there's a neat way to evaluate them when n is a power of 2. So what do we do there? We decompose p of x into 2 parts, one for the even terms and one for the odd terms. So let's say p of x is this. We split the terms. We group the even exponent terms and then the odd exponent terms. So we'll get something like this. And then if we group the odd terms, we can extract 1x from it. So we get something like this. And now we get an expression like this, where let's say e is some polynomial and o is another polynomial. We put x squared here because the terms will be x squared, will be even. Yes? Yes, you're correct. This is 2 pi ik. Sorry about that. Okay. Now we express it like this. And let's say we want to evaluate it at some root of unity. And let's say n is a power of 2. If you square it, what you'll get is you'll get is an n over 2 root of unity. Okay? If you square up an nth root of unity, you get an n over 2th root of unity. Okay? And then you get something like this. And the nice thing about our nth roots of unity, and if n is even, if you square them, after you evaluate it for half, this one will repeat. This one will repeat as well. Only this will change. Okay? Specifically, this will change. This will become a minus. Okay? So what we do is, for polynomials E and O, we evaluate it recursively with FFT, and then use their evaluations to compute the FFT of P. Okay? So all in all, we have this recurrence. Let's say T of n is the running time. We have a recurrence like this. And then the combined part takes O of n time, because after evaluating those two polynomials, we can compute each of these with just a few operations each. Okay? A fixed number of operations per n. So this is similar to the merge sort recurrence, and this is clearly O of n log n. Okay? And when implementing this algorithm, it's fine to use complex number arithmetic. In some languages, there are built-in libraries to do that. But if not, you can easily implement. Right? If you just declare a class with two parts, the real and imaginary part, and then define addition, subtraction, multiplication on them. Okay? So let's say if you want to multiply these, this is just AC minus BD plus AD plus BCI. Okay, so if you have a class, let's say complex, tapos, and then you have you want to define their product. In C++, for example, you can override operators. So we can write something like this. Again, declare it as constant. And then you just return. Let's say you have double xy here. Just return x plus x times other dot x minus y times other dot y. Something like this. Let's assume that complex has a constructor. Okay? So you can implement a complex arithmetic by yourself as well. But in very rare cases, it's also possible for this to not have enough precision to calculate the final answer. Notice that we're computing with doubles this time, and there's no choice if you want to use roots of unity, because other than 1, I, minus 1, and minus I, I think all the other roots of unity will have some irrational real part or imaginary part. Okay? So we have no choice but to use doubles in this case. We can't use a rational arithmetic as well. So it's possible for there not to be enough precision. And this is troublesome in some problems where you need the actual count. Let's say you somehow found a solution for a counting problem, and you need to use FFT, and you need to compute the answers modulo 10 to the 9 plus 7, for example, you might get wrong answer because there's not enough precision. So what do we do if there's not enough precision, or you're at least afraid of that happening?
Basically, we can handle small precision, so we break the polynomial into two parts with coefficients exponent to we write each coefficient as a equal to x into 2 to the power 15 plus some value, and basically use the idea of Recursive.
Can you repeat that?
Basically, each coefficient is ai is equals to x into 2 to the power 15 plus y. Now x and y both are less than 2 to the power 15. This can be easily handled using FFT. And now we just use the combined part similar to the principle, like is x into 2 to the power 15.
Can you write it on the board? I didn't catch everything.
Basically, we write each coefficient as now with FFT we can assume that we are able to handle precision up to 10 to the power 4, like after general FFT take this mode. So basically now each coefficient like which we multiply like can be written as this is suppose x1 2 to the power 15 plus y1. This can be easily handled, but number of FFT calls required would be large.
Okay.
We can do it. And this now we can be taken more the required.
Okay. So thank you. I get it now. So I think what your plan is, split each coefficient into two parts: the big one, the high precision ones, and the low precision ones, or the most significant ones and the least significant ones. And then when multiplying, you do something like this. So all in all, if you do the whole multiplication thing, you'll end up with 4 calls to FFT, right?
4 calls.
You can reduce it with some other tricks, I think, into 3, but.
Like 4 calls, like all inverses. 4 calls.
Yeah. So that's one trick, but it increases the number of FFT calls. Okay, so there's actually other ways to ensure exact values without doing this. Okay, and it relies on the special properties of your modulus. That's why in many FFT problems, you'll usually find a very specific modulus that's not equal to 10 to the 9 plus 7. Okay? So what is this? Notice that all FFT needs is a root of unity, an nth root of unity, more specifically a primitive nth root of unity. What I mean by primitive, it means n is the smallest exponent, which you can raise it to 1. Okay, so let's say I is a primitive 4th root of unity. If you raise it to 4, you get 1. But there's no smaller exponent which you can raise it to 1. Okay, except 0 again. Negative 1 is also a 4th root of unity, but it's not a primitive 4th root of unity because you can also raise it to 2. Right? Now, all FFT needs is a primitive nth root of unity if you want to do an FFT of size n. Okay? And usually n is a power of 2 if we are doing FFT, right? Therefore, we usually want some primitive 2 raised to kth root of unity. Okay? But in some moduli, those numbers exist. For example, mod 11. First, notice that by Fermat's little theorem, we have this equality, right? Therefore, all numbers are a p minus 1th root of unity. Of course, not all of them will be primitive. Okay, so the question is, will there always be a primitive p minus 1th root of unity for any prime p? Yes. Why?
We can prove that their total number is pi of p minus 1.
Okay. How?
This is not this. Basically, we consider all the numbers which are congruent to pi of p minus 1, and we can prove that they will generate, like they are generated.
Okay. So the main idea of the proof. So remember this one. This is the Fermat's little theorem. This is true for every a in this range. Okay. So every number is in fact a p minus 1th root of unity. Now the question is there a primitive p minus 1th root of unity? And the answer is yes. So why? So let's say we do this. This is not a rigorous proof, by the way. I don't remember the exact proof, but notice that this is a polynomial of degree p minus 1, right? So, and we have found those p minus 1 roots. So, what else can we do? Each number is a root of this, but let's define ord a as the minimum exponent of a, which you can raise to get 1. Okay? And then let's call f of k as the number of a such that ord of a is k. Something like that. Okay? We can easily prove that the order of any number a is a divisor of p minus 1. So let's say we collect all divisors of p minus 1. So what we get is something like this. F of d for all divisors of p minus 1 is equal to p minus 1. Okay? So I think from this, I don't remember the next step, but I think you can prove here that there will in fact be at least one number for each f. In other words, f of d is greater than equal to 0 for every p, or for every d. I mean, it will be strictly greater than 0. So what happens here? I think what we can do is, if we factorize this somehow into multiple polynomials, let's say we have x fourth minus 1, we can factorize that into x minus 1, x plus 1, and x squared plus 1. Okay? So what are these polynomials? They're called the cyclotomic polynomials, and the roots of them, for example, this one, this is the fourth cyclotomic polynomials, and its roots will be the primitive fourth roots of unity. Okay, so so if you have something like this, you can factor it out, something like that. If we write each, we can factor out this polynomial into something like this, where this represents the cyclotomic polynomials. Okay. The thing is, you can also do this factorization mod p, I think, and then I think from that you can show that they will have the same roots as this polynomial. Okay, so I don't remember the proof. I didn't. So I suppose you just try to read up on it. But but you can actually show that there is indeed a p minus 1th root of unity for any prime p. Okay. So what does this mean? Let's say you have a primitive p minus 1th root of unity. Let's call it g. If you consider this sequence, taking everything mod p, okay, until g of p minus 2, then you get distinct elements. Okay? Of course, when you do g raised to p minus 1, you get equal to g raised to 0. But before that, you get distinct elements because g is a primitive p minus 1th root of unity. Okay? You cannot have two equal elements here because that would mean g raised to, let's say, I minus j is equal to 1. And you have found a smaller exponent, I minus j. Okay? So what does this mean? Notice that, let's give an example. Let's say p equals 11. And let's find some generator, G0, G1, G2, G3, G4. Remember that G is a primitive 10th root of unity when p equals 11. Now, if you take G squared, this number, then this will be a primitive 5th root of unity, mod 11. Because all these numbers are distinct. But if you reach g raised to 10, then you've raised this number to the power of 5, and therefore you get a primitive 5th root of unity. You can also find the primitive square root of unity. Just take g raised to 5. Because if you square it, you get 1. Remember, g raised to 10 is 1. Okay? So what does this mean? In fact, for any divisor of p minus 1, we can find a primitive dth root of unity. With other arguments, you can also prove that those are the only primitive roots of unity you can find. Okay, so first we have proved that for every divisor of p minus 1, d, we can find a primitive dth root of unity. You can also show, using other arguments, that there are no other primitive roots of unity. The only primitive roots of unity mod p are those which are divisors of p minus 1. Okay, so that's why, remember, if we're doing FFT, we're looking for a primitive 2 raised to kth root of unity for k large enough. That's why in FFT problems, you'll usually see moduli like, let's say, something like this. Of course, it's not 10 raised to 9 plus 7, but if you factor it out, I mean subtract 1 and factor it out, you'll actually see that it's of the form 2 raised to k times something. Okay, so that's a modular. So the modulus itself looks like something like this. What does this guarantee? Remember that if this is p, then p minus 1 will be something like this, which has a large power of 2 as a factor. Therefore, you can find some primitive 2 raised to kth root of unity, which enables you to do FFT modulo that prime. Okay? That's the only thing about it. And the whole algorithm works. The only thing remaining is just to find the primitive 2 raised to kth root of unity, but the whole FFT thing works. Just replace the multiplication and division with modular multiplication and division. Okay? Subtraction, addition, everything works. Okay? So the problem is, how do you find such a root of unity? Just, for example, you have some p. How do you find 2 raised to kth root of unity? Let's say p is of that form. What you can do is first find the primitive p minus 1th root of unity. It's called what? Yes. So just find the p minus 1th root of unity, a primitive one, and then raise it to the power m. Okay, what you get is a primitive 2 raised to kth root of unity. The only question is, how do you find a primitive p minus 1th root of unity? Remember in our example before, let's say p equals 10 or p equals 11. let's assume that g is a primitive 10th root of unity. Now you want to find the primitive 5th root of unity. You square it, okay? If you want to find the primitive 2nd root of unity, you raise it to the power 5, okay? So it's a very similar, it's a generalized form in this case, okay? We want to find a primitive root of this exponent, so we raise the generator by this exponent. Okay, the question is, how do you find that number? Just trial and error. Just find something. You just have to know how to check if it is a generator or if it's a primitive p minus 1 root of unity. Just check all divisors of p minus 1. Okay, factorize this number. Check, raise your number to all those divisors, and check that this is the only thing that works. This is the only exponent that yields 1. Okay. So this strategy is not bad because we can prove that the number of primitive p minus 1 root of unity is this number, Euler's totient, and this is not bad. Okay, there are a lot of primitive roots of unity. So just try them at random, or just try them one by one, 1, 2, 3, 4, until you find one, and then do the whole thing, FFT. Except you're not using complex numbers anymore. You're using that number that you got. Okay? So, of course, we cannot use this notation anymore. That's why in many treatments they use omega sub n, so that this stands for a primitive nth root of unity. Okay, regardless of whether you're working with complex numbers or working on a finite field or something. So, and I think that's what's being called as the number theoretic transform. It's basically FFT, mod sum prime. Okay? So now, let's discuss some applications of FFT. But first, what else can you do when you know how to multiply polynomials quickly? If you can multiply quickly, can you also divide quickly? What's the naive algorithm? What's a slow algorithm of dividing two polynomials? You can do long division, determining the leading exponent each time and then adjusting everything. Okay? But can you do it faster? That algorithm takes O of n squared, where n is the degree of the polynomials you're dividing. Okay, so when you want to divide, there's actually a way for you to reduce polynomial division into polynomial multiplication. So how do we do that? So first, let's say we want to divide f of x and g of x. Okay, note that the division may not be exact. Okay, you might have some remainder. So you have some quotient, but you may also have some remainder. In general, we can express it as something like this. Q of x is the quotient that we're looking for, and R of x is the remainder. Okay? And we require that the degree of R is less than the degree of G for it to be the remainder. And we can show that there's a unique way to write, there's a unique Q and R pair for this equation to hold. And now we're looking for the quotient and the remainder. By doing so, we can actually both compute polynomial division, and we can also compute polynomial modulo. Let's say you need this somehow. In our one of our first sessions, we actually need to compute this. So how do you compute this? So to recap, F and G are our inputs. We're looking for Q and R, and we want degree of R to be less than the degree of G. Here is to reverse F and G. So let's invent some notation first. Let's write f prime of x as the reversal of polynomial f of x. Okay, so let's say let's say you have f of x equals 2x squared minus 3x minus 1. Then f prime of x will be minus x squared minus 3x plus 2x squared, or 2. Okay, we just reverse the coefficients. If there are zeros there, you have to include them in your reversal. Okay, this is not the derivative. Okay, we're just using the same notation for now because we don't need a derivative. We can also express the reversal as something like this. So, what's the motivation for this one? This is the degree of f, by the way. Because if you substitute 1 over x, then you almost reverse the polynomial. You just have to multiply it again, so it becomes a polynomial, right? So for example, try it here. If you replace this by 1 over x, and then multiply everything by x squared, then you indeed get this, right? So we have this expression. Okay? And now, let's try doing reversing everything. So we have something like this. I'm just replacing each of those with the reversal. So what do we do next? Notice, remember that we're looking for this, right? The next step, what I can do is replace x by 1 over y. Okay? Y is another variable. I'm just taking everything in reverse. So if we do that, then you'll have 1 over y everywhere. Let's also multiply everything by some amount. But let's do that later. Let's combine these. Now let's multiply all sides by this quantity. Okay, let's multiply all sides. So this one will disappear. And now this one will become y, degree of f, minus degree of g, minus degree of q. But notice that this is equal to the degree of f by the way we defined g and q. Okay? Therefore, it will disappear as well. Now we get something over here. Minus degree of r. So we get this equation. Remember that the degree of r is less than the degree of g. Okay? Let's take this equation modulo this polynomial, or this term. So we have this term. And we have this congruence. Okay? I just reduced everything modulo this value, which is a polynomial. But notice that degree of r is less than the degree of g. Therefore, we can show that the degree of f minus the degree of r is greater than or equal to the degree of f minus the degree of g plus 1. Okay? So we can further reduce everything modulo this value, because this one is a divisor of this one. So let's just replace this one by degree of f minus degree of g plus 1. Okay? And now, remember we're looking for q. We can compute q, the reverse of q. If we compute the reverse of q, we can easily compute q itself by just reversing the coefficients. But what do we see here? We see that q prime is this times the inverse of this mod this value. Okay? So that's it. If we want to compute the quotient, just take the inverse of this polynomial, the reversal of g, modulo this, and then multiply it by f using f of t. Right? So first take the inverse, which will be some polynomial because of this, and then multiply them, and you get q. Okay? And that's enough because the degree of q is at most degree of f minus degree of g. So by doing that, we actually get all the coefficients that we need. The question now is, how do you compute the inverse? Okay? To compute the inverse, we can use a technique very similar to Hensel's lifting, because this is y raised to something. Okay? So let's say we have some polynomial, g of x, and we want to compute its inverse modulo some x raised to k for some k. So let's say we want to compute this. The first step is to compute it mod x. And then to compute it mod x squared, and then mod x raised to 4, mod raised to x to 8, and so on and so forth until you get something larger than x raised to k. When you do that, you get enough terms that you need. So the first step, how do you compute it modulo x?
Doesn't Hensel's lifting increase by 1 rather than multiplying?
Yes, but we're doing an accelerated version of Hensel's lifting. Okay? You can also do that with the actual Hensel's lifting. There's also a way to accelerate that by doubling instead of increasing by 1 every time. But
can we do this here also?
yeah, that's what I'm saying. I think there's also a way to accelerate the actual Hensel's lifting method. But in this case, let's do it with polynomials. So what happens here? How do you compute this? If you take everything mod x, then this is just a constant. This is just a constant term of g. And to invert it, just take the inverse. Okay? If it's a complex number, just take the reciprocal. If you're doing it mod p, then take the modular inverse mod p. Okay, so this one is very easy. Now, what do we do? Now, what do we want? Let's say you have g inverse mod x to the n for some n. We want to compute g inverse mod x raised to 2n. Okay? Any polynomial mod x reduces to just its constant term, right? So just take its inverse, and now you have this. Okay?
So shouldn't it be like g of x inverse mod x is defined as the inverse of g of x mod x, or the mod of g of x inverse? Like there's a difference.
There's no difference.
So how
Remember, when this symbol is qualified, okay, usually when we write something like this and we write mod, then we usually associate -1 with the modulus. Okay? So this actually means the inverse, the modular inverse of this mod x. So you take g of x mod x first. Okay? Why? The question is, why does that work? The only important claim here, let's say you have computed the inverse of some polynomial mod xn. Then if you reduce that mod xn minus 1, then this is still an inverse. If you reduce that answer, then that's also an inverse of g of x mod n minus 1. Okay? And for the same reason, if you have something like this, a sub x If you have something like this, then it is also true that this is true. Something like that. Okay? Or no. That's not the best example. Let's say you have some polynomial, g of x. My claim is, first reduce it mod x n minus 1, and then take the inverse. You'll get some polynomial. The second, first take its inverse, mod xn, and then reduce that answer mod xn minus 1. My claim is that those answers will be the same because, let's say you have some polynomial, okay? So g of x, you can write it something like this. Until this. You don't need the extra terms because we're doing everything mod xn. And now let's say you have found the inverse. You can write it as well as something like this, right? Now, of course, if you multiply these polynomials mod x raised to n, you'll get 1 by definition of inverse. But if you reduce them mod x raised to n minus 1, you'll still get 1, okay? That's why if you reduce g of x mod n minus 1 first, then you'll get the same inverse. Okay? It's the same here. So we're looking for a an inverse of g of x raised mod x raised to k. Okay? If you reduce everything mod x, then you'll get the inverse of g of x mod x. Okay? So the question is, how do we lift? Let's say you have computed the inverse mod x raised to n. We want now to compute this value. Okay? So let's say the polynomial that you were able to compute is h of x. Let's say this is the inverse of g mod x raised to n. The degree of h is less than n. Okay? But now we want to compute the full inverse. The problem is this polynomial might not work because the first few terms will it will indeed be 1 for lower order terms, but then you'll get some extra terms somewhere here. Okay? That doesn't appear mod x raised to n. So what we want is to adjust x raised to n, adjust the inverse that we have. So g of x is really h of x plus x raised to n times some other polynomial j of x. Okay? This is the adjusted term, and we're looking for j. Let's say we already have h. We're looking for j this time. So how do we compute j of x? Remember that we want it to be an inverse of g of x, so we want this product to be 1 mod x raised to 2n. Okay? Let's try solving for j of x. What do we get here? Something like this. Okay? But notice that this will be divisible by x raised to n because we have computed h as the inverse of g mod x raised to n. Okay, so if we subtract 1 from that, or if we subtract that from 1, then the remaining terms will be divisible by x raised to n. So let's divide it by x raised to n. Okay? And then we divide the modulus by x raised to n as well. Now we're solving this equation. First, we can do this multiplication using FFT. Okay? And then just divide by x raised to n. And now we want to compute the inverse of g, but we already have that. That's simply h of x. Therefore, j of x is simply this thing, 1 minus g of x, h of x, over x raised to n, times h of x, mod x raised to n. So this is it. Let's say you have computed h of x, which is the inverse mod x raised to n. You just need to compute two polynomial products using FFT. And then you get j of x, which is the extension of the inverse. Okay, the additional terms that you need. And then keep repeating that, doubling and doubling until you have enough terms for the inverse. Okay? Once you have enough terms for the inverse, now you can compute the quotient as this. Actually, this is just the reverse of the quotient, so you reverse it. And then you now have the quotient. To compute the remainder, or the modulo, you just do something like this. If you have all of this, you can use FFT to compute.
Finding the inverse would require n log square n.
So yeah, the question is, how fast does this run? Of course, it depends on the number of multiplications, the size of the multiplications. So let's calculate that. In this step, we're doubling where we have n. We needed to multiply 2 times with polynomials of size of degree n, right? How fast does that run? N log n, using FFT. But we start at 1, so you have something like 1 log 1 plus 2 log 2 plus 4 log 4, okay? Because you're doubling in size until 2 raised to k log 2 raised to k. Okay, let's just say this is n. Okay? We can replace the numbers inside log as n. And then combine everything. It will become 2n log n. Or just O of n log n. So computing the inverse is actually n log n. Even though we did multiple products here, because their sizes are doubling, the overall complexity is still O of n log n. Okay?
So,
Yes?
can't we do this, that is my fx by gx you want to find essentially. So can't we do that by some online FFT kind of algorithm, like the highest power you know and then put like
Yeah. Yes, I think you can do that, but there will be an extra log factor. Okay? Because the online FFT thing, I think has a log squared factor instead of just this. But this one is just n log n. There are lots of products, but overall it's still n log n. Of course, the constant is still large. Okay? In the last step, you'll multiply 2 big polynomials, and then there's a lot of other products here. So the constant will be large, but it's still O of n log n. Of course, if you're taking modulo, there's another product. But that's fine. Okay? So that's one way to compute polynomial inverse and polynomials, and how to take polynomial modulo another polynomial. So essentially, we have reduced polynomial division into polynomial multiplication. Next. What else can we do with FFT? With FFT, we can solve this problem. Let's say you have some polynomial p of x, and then you want to evaluate it at n points. So how do you do that? Yes?
I want to ask, suppose you take modulus of polynomial, modulo of a polynomial with x, and you got a constant. So how will you take it inverse, constant inverse modulus?
If you're doing complex numbers, just take the reciprocal. If you're doing it mod p, then take the modular inverse mod p.
But we are doing it modulo x.
Modulo x and modulo p as well. Okay? Remember, we're doing it mod x, but we're doing everything else. The coefficients are living in some field. Okay? In the normal case, where that field is simply the complex numbers. So if you want to take the inverse, that's just the reciprocal. But sometimes your polynomial has coefficients from another field. Let's say modulo p. And in that field, the inverse is simply the modular inverse mod p. Okay? So we're taking two moduli here, the p and then x itself as well. Okay? Yes? Okay. So how to solve this problem? Of course, the naive algorithm is to just evaluate them one by one, but each evaluation takes O of n time. So how can we make this faster? The idea here is quite sneaky, I think. Let's say you want to compute p of x sub I. Then this is just p of x mod x minus x sub I. Is that correct? Why? Okay, so we can show this pretty easily. If you have p of x, and let's say you divide it by this, you'll have some quotient polynomial and some remainder polynomial. Okay, where this remainder polynomial will have degree less than this. But this has degree 1, therefore, this must be constant, right? So let's just write r because it's a constant. Now let's say you try to evaluate it at x sub I. This will become p of x sub I, and this will cancel out, right? So you get r. Therefore, the remainder must be the evaluation. Okay? And without doing that manipulation, if you interpret the word mod in the right way, then that should be pretty clear. Whenever you see something mod x, think of it as saying we want x to equal 0. Okay, we're doing everything in a world where x is equal to 0. Okay? So let's say we're doing raising 2 raised to 10 mod 11. What we're saying is we want this value, but in a world where 11 is equal to 0. That's why if you multiply, this is 2 raised to 5 times 2 raised to 5, and then you get 32 squared. But we know we're in this world, so 32 in this world is just minus 1, right? So we can square, so we get 1. Okay? You can interpret mod as saying we want the value inside to be 0. In this case, you can interpret that the same way. So we want x minus xy, x sub I to be 0. In other words, we want x to equal x sub I. And in that world, the evaluation p of xi is simply p of x. Okay? This is an informal thing. This is nothing formal. But when you see the word modulo, what we're really saying is we don't care about this. We consider this as nothing. Okay? That's a good heuristic when reading mod. So now we have this. Of course, it doesn't help that much yet because if you want to do something like this, this will take O of n for each x sub I. But the trick is, first, let's build this polynomial. Okay, how do we build this polynomial, by the way? We can split the product in half, and we have two subproblems of half the size. Okay, and we will get some polynomials. We can multiply those, we'll get this. So we'll get, you can use FFT for that. So the overall complexity will be O of n log squared n, right? Because the combined part takes O of n log n. Now what do we do when we get this polynomial? We take p of x mod that polynomial. Of course, it probably won't help you a lot. Okay? It's possible also that p has a smaller degree than this product, so this will still be p of x. But let's do that anyway. Now, remember that when computing this product, we ended up with two halves of the same product. Okay, and then this one starts at, let's say, a half. Okay. Take this polynomial and reduce it mod this and then mod this. Okay. And then, while computing this product, we also have two halves. Reduce this polynomial mod those two halves. Okay? And so on and so forth until we end up at just single terms like this. So the leaves will actually contain the evaluations that we want. So that's one algorithm of computing p of x in various x. How fast does this run, by the way? Why?
Recurrence is O of t of n equal to 2 t of n plus n of n for finding the inverse.
Okay, that's good. So you're saying the complexity is this, and I think that's correct. Of course, the first part itself, computing these polynomials, already take this much. But the other part of going down also takes that much. Why? Because let's say you have some polynomial. After this operation, p of x will be of degree less than n. Okay? So we're taking some polynomial of degrees less than n, modulo a polynomial of degree n over 2, approximately n over 2. After this process, you have a polynomial of degree n over 2 on both sides. So the sizes actually have, as you go down the binary tree. So you can get the similar recurrence. So you'll also get n log squared n. And that's faster than n squared. Okay?
So like even when you're taking the modulus, so you will just take the answer of the left and the right side and then just product them.
No, so in this algorithm, there are two parts. First, calculating these products, and then taking the modulus downwards. Okay?
First we will compute only the x minus xi that product.
Yeah.
Then we will take the modulus.
Yes, and then go down, and you already have this product. So you take the modulus. Okay?
So essentially you will be first time creating that structure and then traversing that.
Yes. Okay? What else can we do with FFT? This is we're just discussing the standard things you can do assuming you already have a fast polynomial product. So we have discussed evaluating a polynomial in multiple x. Now let's discuss interpolating. Let's say you have n points. You want to find the polynomial of degree at most n, which passes through all those points. So how do we do that? How do we do that naively first? Slow solution. There's an n squared algorithm. And what's that algorithm? So that algorithm uses some trick. Let's say we find some polynomial phi I of x. So let's say we find some polynomial phi I of x which evaluates to 0 on all of those x's except x sub I. Okay? If you evaluate it to any x sub I, you will get 0 except this in this x in particular. You'll get some value. We don't care yet what that value is. Okay? If we have such polynomials, then we can actually get the answer right away. Let's just get the first one. Okay, and then divide it by phi1 x1, and then multiply it by y1. What does this polynomial mean? Notice that these are constants. Okay, so this polynomial evaluates to 0 at almost all x except x sub 1 itself. And in x sub 1 itself, you get y1. Okay? But if we do that for all indices, then we get the answer, right? Because let's say you have x sub I. If you evaluate this polynomial in x sub I, what do we get? Everything else will become 0 except the term, the ith term, right? And in the ith term, you'll get y sub I. So this one is correct. So the only problem now is finding these polynomials. So the question is, let's say, how do you build a polynomial which is 0 on everything except x sub I? That's pretty simple. Yeah, just multiply these terms, but skip the ith term, right? If you have that polynomial, then it evaluates to 0 in almost all terms except the ith term, okay? And to evaluate this, well, you can use an n-squared algorithm. So actually, you'll have an n-cube algorithm to do this, right? Because it takes n-squared for each. But we can also do it in n-squared by first taking this product and then divide it by x minus x sub I. Okay, dividing by this term is just O of n. So compute this term in n squared, and then divide it in O of n each. So everything else is in O of n squared. But can we do it faster than n squared?
Why is the 9 one n square? Because we want to evaluate it at a point, not multiply the polynomial.
What?
Do we need to get the actual polynomial or want to evaluate given another?
So we are discussing the problem of interpolating these points. So given n points, we want to find the polynomial that passes through them. Okay, so can we do it faster? So I think we can do it faster. So let's take the case n equals 4. So we have this polynomial. So for n equals 4, you'll have something like this. Times some constant, let's say alpha 1, plus x1, x minus x1, x minus x3, x minus x4, alpha 2, plus x minus x1, x minus x2, x minus x4, alpha 3, plus x minus x1, x minus x2, x minus x3, alpha 4. Okay, so the answer will be of this form somehow. Okay? The thing is, we can split it somewhere here, somewhere in half. And notice that on one side, you have a common factor, x minus x3, x minus x4, right? And then in this other half, you have a common factor, x minus x1, x minus x2. But in getting these polynomials, you remember the divide and conquer thing we did? We can use the similar technique. The only problem is how do we combine them so we can compute the actual answer. So the main idea is we take this product and split it into two. And then the idea is to combine the answers somehow so that we get the answer that we want. Let's call this S of x, S1 of x. And let's call this S2 of x. So what do we want here? We know that the answer will be of this form. So some polynomial, let's say f sub 1 of x, s sub 2 of x, plus f sub 2 of x, s sub 1 of x. Okay, because we know that the left-hand side has this as a common factor and the right side has this as a common factor. Now we're looking for f sub 1 and f sub 2. Now, let's say you want to evaluate it at some x sub I. And let's say for example, x sub I is less than, let's say I is less than or equal to n over 2. Okay? So x sub I appears in this product. Okay, so we have s of 1 x sub I is equal to 0. So if we evaluate this at x sub I, then we get this part to be 0. Yes?
Why are we considering this product, like to find the polynomial?
Remember, when we, in the n squared algorithm, remember I wrote down the whole answer, for example, for n over 4. If we split it in half, then the left-hand side has some common factor, and the right-hand side has some common factor. And in fact, the common factor in the left-hand side is this, and the common factor in the right-hand side is this. Therefore, we know that the answer is of this form. Okay? The only question is what is f of 1 and what is f of 2? Okay?
But we need not we don't need to evaluate the product, right? Like x minus x1 up to x minus x. We need to find the remainder also by division with x minus xi. So how would we adjust that?
But why do we need the remainder?
Because the polynomial, like the answer of this question is represented by that term.
So remember that we're trying to find the polynomial itself. Okay, we're given endpoints. So I don't see why you need the inverse somewhere or the remainder somewhere. Okay, so what am I saying here? P of I of x, we defined it as x minus x1, x minus x2, but we skip the nth term. So if we take the whole product, we're actually dividing it by this, okay? And the final answer looks something like this, okay? A sum of terms that's similar to this. I abbreviated it as some alpha 1 because they're just constants. Okay, so the whole solution will look something like this. Okay, now consider this sum until the nth term and split it in half somehow. Okay, the sum, split it in half. Okay, remember how each phi of I is formed. Therefore, all the terms in this, if we take the product, something like this term will divide each of these terms. And the products here will divide each of these terms. That's what I'm saying. Therefore, we know that the answer will be of this form for some f and f sub 1 and f sub 2. The only question now is what is f sub 1 and f sub 2? We're trying to look for that. Okay? What are we looking for? We want a polynomial that evaluates to these points. Okay? Now, consider some x sub I where I is less than or equal to n over 2. Since I is less than or equal to n over 2, this polynomial, when evaluated there, will be 0. Right? So this part will be 0. And then we get f sub 1, x sub I, f sub 2, x sub I. Right? And we want that to equal y sub I. Right? So this is true for this range. Similarly, if you take the other range, you'll get this equation. Okay? Now let's try to divide. Let's divide it. Y sub I, s sub 2, x sub I. And this one, y sub I, s sub 1, x sub I. Now we're looking for a polynomial f1 that evaluates to each of these points. And we can do that recursively using the same multi-point evaluation algorithm. But to do that, we need to evaluate s sub 2 at these points. we can use multi-point evaluation for that. Okay, so the first idea, for all I, evaluate x sub I on this polynomial using multi-point evaluation. And the next, compute f sub 1 using polynomial interpolation, where the values will be this, recursively. We can do that as well for s sub 2. Now you have f sub 1 and f sub 2. Just take the product using FFT, and you have the polynomial that you want. Okay? So we're using the algorithms that we have built before, namely a polynomial interpolation recursively, and evaluating a polynomial in multiple points. Okay? Any questions? Of course, the constant of this algorithm will be very high, but you can also prove that everything takes n log squared n time.
Log because multi-point evaluation is log square and
I think this part is repeated in all parts of the algorithm. I think the naive ways will be n log cube n, but I think there's a way to reduce it to n log squared n. So I don't know. Let's just say n log cube n. Okay, that's safe and that's correct. But let me see. Oh yeah, that's safe. N log cube n. So not only is the constant very high, but there's a lot of log factors here. But at least it's better than n squared theoretically. Okay? So that's it. That's polynomial interpolation. If you can reduce one log factor, then that would be nice. Okay? I haven't implemented that one actually. I just know that it can be done. And I know that it's not that useful because of the high constant factor and lots of log factors there. Okay, so if you can reduce the log factor and you have some ideas, that would be nice. Yes?
It's like a Strasson's algorithm, which is theoretically better, but it is a high constant.
You can say that. So it's kind of like Strasson's algorithm because the constant will be high. Okay, so I guess after discussing those polynomials, let's find some example problem which uses FFT somehow. So first, a simple one. Let's give an example. Let's say you're given you're given n numbers, x sub 1, x sub 2, up to x sub n. Okay? And your goal is, for each k from 1 to n, for each k, first find all the k-tuples of distinct elements from this array, and then find the sum of the products of all those k-tuples. Okay? So that's the problem. And then everything modulo some prime. So for example, n equals 3. So we have 3 numbers. So for k equals 1, the answer will be simply the sum. For k equals 2, the answer will be x1, x2 plus x1, x3 plus x2, x3. For k equals 3, the answer will be x1, x2, x3. So the problem is, given this array, calculate all of these sums of products. Mod sum prime p.
because of the polynomials x plus x1, x plus x2 and then multiply.
Yes, so that's it. Just compute this product.
For k, it would be n minus k. Like,
What?
for finding k equal to 1, we would have to take the coefficient of n minus k.
Yeah, so just take this product, and then these will be the coefficients, right? So how fast does that run?
How do we guarantee that all the k-tuples are distinct?
Let's say you want to compute the coefficient of x sub I, or let's say x sub n minus I. To get a coefficient of x sub n minus I, you have to select n minus I x's from n minus I terms, and for the remaining ones, select their constants. So that will be a product of distinct terms. Okay.
All the elements of the array are distinct?
Oh, I didn't state it quite formally, but I only want the indices to be distinct. Okay. Yeah. So this algorithm will be n log squared n because remember we needed to multiply something like this before, and we can do that by divide and conquer as well. Okay. So next problem. So in the next problem, you're given two strings, S and T, and the length of T is at most the length of S. The question is, how many times does T appear as a substring of S? The lengths will be up to, let's say, 10 raised to 5.
Is there any constraint on the number of characters in S and T? Because
What?
number of distinct characters in S and T, like the alphabet, like
Let's say the alphabet is English lowercase letters.
so we can do 26 FFTs and like for each position find like how many times A will occur and create a polynomial for that. In case the number of alphabets is less, it would be.
Okay. So if the alphabet is not that small. Okay, so you're trying to force FFT into the solution.
I have done this problem.
Okay. So how do we solve this problem? Of course, this problem is a very standard one. You can just use KMP or other algorithms. But I'm mentioning it here because there's an FFT, a solution that uses FFT. So how do we do that? Let's first assume that instead of strings, that there are arrays of numbers. Okay? And so there will be numbers from 1 to 26 because we have lowercase letters. So S sub S will be, so let's say S0, S1, up to S sub n minus 1, and T will be T of m minus 1. And now let's say we want to check if T appears in S starting at the ith position. How can we check that? We can check that by computing this sum. Okay? So what does this sum do? If T indeed appears in position I, then this sum will be 0 because each of these will be 0. But if not, then it will not be 0 because at least one of these will be non-zero, but they're all non-negative numbers. So this will be, you have this inequality. So if at least one character doesn't match, then this sum will be strictly greater than 0. If all of them match, then this will be equal to 0. So what we can do is just to compute this value for each I and just count the number of zeros. That will be the number of occurrences of T in S. But how do we compute this? So let's write it in something like this. So it's equal to this, right? Let's try expanding everything. Okay? And now we have three sums. This one is easy to compute beforehand because this is just the sum of squares of the values of t. So this one is easy. And this one is it's easy to compute as well. This one is easy to compute. This is just the sum of squares for t. Okay? This one is a range sum on the squares of s. Okay? So we can compute this sum in O of 1. The only thing remaining is this sum. And this is a convolution. Why is it a convolution? So remember, before when we had some sum like this, then we were able to compute it into an FFT, into a polynomial multiplication, because this is precisely the coefficient in the product of two polynomials, right? But this one is a little different because there's a plus j instead of a minus j. So what do we do here? So let's reverse. So it's almost a convolution, except there's a plus instead of a minus. We can easily reverse s, for example. And then if we reverse s, let's say s prime is the reverse of s. Then this one will simply be this. And now we have a minus. Of course, this one will be a little different, but that's fine. If you multiply t and the reverse of s, then just access this index, and you'll get this product. Okay? And you'll get this product in O of 1 after computing the product. Okay? So that's one way to use FFT in string matching. Okay, the algorithm takes n log n time because you need to multiply two polynomials of that size, almost of that size. But after that, everything else takes O of n. Now, let's make the problem a little different. So, for example, the problem is you still have two strings, s and t, lowercase letters, but now t can have a dot character. And a dot matches any character. Now the question is, how many substrings does t match this time? Okay?
So it can have exactly one dot.
It can have any number of dots. So if everything is dot, then every substring of size m matches. The alphabet size is, it can be large, it can be small. So what?
We can take the dot to be 0, and like while computing those sums, SI squares, we can take care that.
We can
Just remove that term, like there will be one moving term in between which is removed always. So we are computing all the SI square sums m minus 1. So we will be removing only that SI square where dot comes.
How can you remove that? So remember we had this sum, okay? For the ith position, we need to compute this. Now, what do you intend to do with dots again?
If I take dot to be 0, t dot to be 0, then I should subtract SI plus the dot's position square.
Okay. So that's one possibility.
That should be only one term.
So you have something like this. Something like that.
Many dots are there.
Yeah, so this basically says that this is 1 for every position where the j is 0, and this works, right? So yeah, this is another FFT, right? This is another convolution, okay? Another thing you can do is this. If tj is 0, then that will disappear. If tj is not 0, then it will be multiplied by some constant, but it's still non-zero. That's the only thing we need to know. And now what do we get here? Okay, so this is now the sum of cubes. And now we have two FFTs. Okay, still two FFTs, but this is nice. Okay? It's easy to adjust as well if there are dots in S. Okay? In this case, you can just add Si plus j here. Okay? So that's an example on how to use FFT on strings. Okay? You just
For that sum is I plus j whole square is j.
So in this one, you take the squares and consider that as one array, and then you take t, and then multiply those polynomials.
So like in the previous case you were just reversing the string and
So just compute this array, and then this array, turn them into polynomials and multiply them. Okay? Of course, you can also do this. You can choose your modulus to be some random prime that's large enough. And that has a modular 2 raised to k root of unity, so you can do FFT on it. And then check if the number is not equal to 0. Okay? If you're afraid that that might fail, just use many primes p. Okay? So your chances of failing this time is similar to the chances of you failing in hashing problems as well. Okay? So in that problem, one important lesson is you should be able to recognize convolutions as something like this and as something like this. If you have something like this, you can reverse one of the arrays and it's still a polynomial multiplication. Okay? Another hint, somewhat, is if your modulus is weird, then try factorizing mod minus 1. If you can find a large power of 2 in it, then it's possible that the intended solution is FFT. But don't rely on that observation. Okay? At some point, it's going to get too common, and then authors will start using a modulus that always has that factor. And then you're not sure anymore if FFT applies.
They did that
Yes.
in SmackDown finals. They had
Yes.
free talking stuff like that.
Yeah. So they used a weird modulus that has that power. And in fact, there's no problem that has FFT. The hardest problem, there's an FFT solution, but it's too slow. So the intended solution is just a formula. Right? So be careful nowadays. Okay? Before, it's a good hint that FFT will be applied. But maybe at some point, this modulus will become obsolete and we'll now use every time an FFT-friendly modulus. Okay? What else? Okay, so in other cases, you're required to multiply polynomials, but the modulus doesn't have a modular 2 raised to k root of unity. In those cases, it's still possible to compute the product, except we'll have to use more FFT calls this time. But how exactly do we do that? Let's say your modulus is 10 raised to 9 plus 7, and you need to multiply 2 polynomials.
That trick will
What?
reducing the
A what?
Reducing the coefficients trick will reducing the coefficients possible trick.
Okay. So the trick you mentioned, I think that will work. But you'll get 4 FFT calls. Depends on the modulus. You can get fewer calls. Okay. So in some cases, you'll find a very small modulus. You might see this. It's a prime, but it's not friendly to FFT. But let's say you need to multiply 2 polynomials mod this prime. The first thing to notice is, first, try to reduce the coefficients of your polynomial mod this. Therefore, the largest coefficient that you have is at most 1 million plus 3, or 1 million plus 2. Okay? Now, the simplest algorithm is to just multiply the polynomials exactly without a mod. And then after doing that multiplication, just reduce everything mod this. That will be correct.
How can we reduce the coefficients modulo this sign?
Just take every coefficient mod this.
No, I mean, like, why is that correct?
Well, if you're trying to multiply 2 polynomials mod this, then of course it's going to be correct to reduce the coefficients this mod this first, right?
Okay, coefficient. I thought.
Okay? So now you have 2 polynomials. You reduced it mod this, and now you multiply those 2 polynomials exactly, and then reduce the coefficients mod this. Okay?
Even if we didn't reduce them modulo that before, then also you could do this normal multiplying and reduce them finally.
Yes, you can do that, but sometimes your coefficients will be larger than this. So we reduce it mod this first just so we can have smaller coefficients. We have a guaranteed upper bound on the coefficient, which is this number. If we don't do that, you can still multiply the polynomials exactly, but you'll have larger coefficients, and we need that bound on the coefficients in this algorithm. Okay? So in this algorithm, we want to multiply 2 polynomials, and we know that the coefficients are at most this number. Let's say this is m, so each coefficient is less than m. So what can we do here? Of course, you can multiply them exactly using complex number arithmetic, but it might be possible to overflow, especially given numbers of this magnitude. For example, let's say the degree of the polynomials you're multiplying is n. So what's the largest coefficient that you can get? The worst case will be if all coefficients will be m minus 1, right? And then the degree will be n. So in one of the coefficients, you'll get this term. Okay? You will get this coefficient, or approximately nm squared. So this will be, if n is, let's say, 10 raised to 5, then this will be 10 raised to 17, which I think exceeds the capacity of double precision numbers. So you'll get in trouble, especially if you need the exact numbers. Okay, so we want to avoid complex number arithmetic. What we can do is to use this bound. This is the maximum possible coefficient that we can have. Okay, so what we can do is to choose a prime much larger than this, and do FFT mod that prime. Okay? We can also choose that prime to be larger than this. At the same time, it has to be FFT friendly, so it has to be of the form 2 raised to k m plus 1. Okay? We can easily find such a prime. And now, do the FFT mod this prime.
It has to be larger than nm squared.
Yes. Do the FFT, use a different variable, let's say alpha. Okay? So, compute the product mod this prime, and you know that the coefficients will be exact because you know that this is much larger than the maximum possible that you have. So, just compute it mod this, and then reduce everything mod this. Okay? Of course, there's a problem in this. As we said, this is 10 raised to 17. So this prime will have so many digits. But you need to multiply and divide mod that prime. So that's hard to work with, especially in C++. There's no big integer, and even if there is, it's going to be slow. In that case, we can do a different trick. instead of choosing a big prime, we can choose several small primes such that their product will be larger than this, at least twice this.
You can multiply two long numbers easily.
Yes, but I just want to avoid that because there's a reason why you always see the modulus up to 1 billion only. You don't usually see a modulus larger than 2 raised to 31, right? Because first of all, that's going to be slower, and it's going to be prone to a lot of overflow problems. Okay, you can fix it, but it's going to be hard. Okay, but I'm describing a different way, which you don't have to do that. What you can do is just select a lot of primes, which are FFT friendly, but whose product is at least twice this, more than twice this number. And then compute the FFT mod each of those primes, and then combine the coefficients using Chinese remainder theorem. By doing that, you get the number modulo the product of those primes. But since the product is greater than twice this, you can extract the exact value by doing that. Okay?
Why are you saying twice of this?
In this case, you don't have to do that. But in other cases where there are negative coefficients, you need the product to be at least twice this. But in this case, since we're computing mod this number, it's enough just to find a product greater than this. Okay? In this case, this is at most 10 raised to 17, so you just need 2 modulus, okay, of around 1 billion in size, and right?
This will increase FFT cost, like if it takes 2, 3.
Yeah, it will increase it to twice, just twice, right? Whereas originally you need 1, you just need 2 now, okay?
You need 2 FFT calls for multiplication.
We can combine both.
Not the FFT calls, but polynomial multiplication calls, I mean, okay?
We can combine them by taking coefficients to the complex.
What do you mean combine them by taking?
2 FFTs we can do by single FFT by taking like real parts as one coefficients and like imaginary part as other coefficients. Then the output we get also, we can say real part will be the coefficients of one thing, imaginary part will be another thing.
Are you using doubles in this solution?
We are doing modules.
So the problem is we don't want to use doubles. You're avoiding it. Okay, so in this in this algorithm, you don't have to do that. So you can just take 2 primes of size around 1 billion, do FFT on both, and then combine using Chinese remainder theorem. If the modulus is a little larger, let's say 10 to the 9 plus 7, then you might need 3. Okay, and then combine them. Of course, it's gonna get tricky if you want to combine 3 values using Chinese remainder theorem, but there are ways to do that, and it's not gonna be the bottleneck of your solution. Okay, it's the number of FFTs that will be the most important. Okay. Sometimes you also need to compute FFT for sizes that is not a power of 2. So far we're computing FFT for power of 2 sizes. If your polynomials don't have a power of 2 size, we can just pad them with zeros, okay? But what if you really need to compute FFT on a size that is not a power of 2? You cannot just pad them, because if you pad by zeros, you extend the length, and then the roots of unity will change. Okay? The roots of unity, the nth roots of unity will not be the same as the n plus 1th root of unity. Okay? Let's say you really need to compute it for a fixed size n. Okay? So you need to evaluate a polynomial mod the nth roots of unity. How can we do that? Okay? So we can write the nth roots of unity as something like this, right? So what we really need to compute is this sum. Okay? So let's say we need to compute this, and we cannot adjust n by padding the sequence. So we can rewrite this as something like this, right? What we can do here is to notice that jk is equal to j squared plus k squared minus j minus k squared over 2. So this is clear? It's clearly jk, right? Now, we can substitute jk with that. So it will be j squared plus k squared minus j minus k squared over 2 all over n. Okay? Yes? What?
On the left side, did you mean to write AK or AI? Or the left side of the, yes, is that supposed to be AI?
Yes, you're correct. It's AK. Thank you. Now we have this. We can cancel the 2, right? And now this is in part of the exponent, so we can split it into terms. So we have something like this. We can factor this out. So we have something like this. And now we have a convolution, right? Except we have additional factors, but we can just multiply that after the process. So if we take this sequence, this sequence, and this sequence, and construct polynomials, then when multiplying them, you're going to get the coefficients that we need, right? But now we are multiplying polynomials together, and we can safely pad zeros this time here, because we don't need to compute a fixed size FFT. So if you need to compute an FFT of a fixed size, you can use this manipulation to convert it to any size FFT that you want. Okay? Finally, we can give another example of a problem where FFT can be used. So in this problem, the problem is going to be simple. Given n, compute n factorial mod p. How do you compute n factorial mod p? Of course, you can do it in O of n by simply multiplying 1 up to n. But I want something faster than doing that.
How big is that?
What?
How big is that?
I just want something faster than O of n. You can say, let's say p is up to 10 to the 9 plus 7. And n can be anything between 0 and p minus 1. Of course, if n is greater than or equal to p, then this product will be 0.
You can use the prime factorization
Okay.
n, like n factorial, like all the powers of prime dividing n factorial, and then calculate the individual mod p, and then multiply.
How? So you need to compute the primes up to n. That takes us.
That won't be too efficient because that is something n by log n.
Yeah. So it's not going to be that efficient because.
Second power will again
the number of primes is almost linear, right? For example, let's say you use the normal sieve, then you'll already take n log n, right? Just for the sieve. Okay, of course there are faster sieves, but you'll only probably reduce this by up to a log factor. Okay? So in this case, there's a sneaky way to do this. So let's say n factorial, we want to calculate that. Let's assume n is a perfect square. Because if not, we can just keep decreasing until we find the perfect square factorial. Okay, and it's not going to be hard to find such a perfect square. Okay, let's say n equals m squared. We have this inequality. So let's say m squared is the largest square, less than or equal to n. Then the difference between n and m squared will be O of m, right? Because the difference between these two are just 2n plus 1, right? So the process of reducing n to a perfect square just takes O of m, or O of square root of n time, and we're happy with that. But now, so what if n is a perfect square? So let's assume n equals m squared. What we can do here is consider this polynomial. Okay? If n equals m squared and we have this polynomial, then n factorial will just be p of 0 times p of m times p of 2m up to m minus 1m. Right? If you substitute 0, you'll get the first m terms of the product, and then the next m terms, etc. Right? But now, we have reduced it to polynomial operations. We have to compute p first with the divide and conquer algorithm. It takes m log squared m time, right? And then we have to evaluate the polynomial at m points, which also takes m log squared m time. So now we have an m log squared m time algorithm to compute n factorial, but m is the square root of n. So this is square root of n log squared n time. Okay? Of course, the constant will be very, very large, but it's a theoretically better solution. Okay? I still don't recommend it. Okay, so this is not the last problem. This is the warm-up problem. So the last problem is given n, you want to count the number of connected graphs of n nodes. And we're only counting simple graphs. So by that, I mean there are no two edges connecting the same pair of points. There are no self-loops. Okay?
This problem was discussed by Satya.
Okay. We'll discuss a faster solution. Yeah. So how do we compute the solution to this?
Consider two designs, like one for finding the number of disconnected graphs on size n, and one on the number of connected ones which we want to find. Their sum would be the total number of graphs, which is 2 to power n choose 2. Now we find the formula for disconnected ones and basically substitute and find it.
Okay. So to solve this problem, first let's define g of n as the number of graphs of size n. So this is easy to compute. This is just this value. You only have to choose for each edge whether to include it or not. In g of n, we're not caring if the graph is connected or not. And now let's also define c of n as the number of connected graphs of size n. And we're looking for that value. Let's also define d sub n as the number of disconnected subgraphs, or graphs of size n. So we have a simple equality, something like this. Okay? But we can also find another relationship between them, a non-trivial one, by considering a single node. If you have a graph, not necessarily connected, consider the nth node. It will belong to some connected component, regardless whether the whole graph is connected or not. Let's say it belongs to a connected component of size k. So how many such graphs are there? First, you have to select like this. Okay? Let's factor out n minus 1 factorial. We'll have n minus 1 factorial here. And then group terms somehow. Okay? Is everything correct? And I don't like n minus 1, so I'll replace this with n factorial over n. Okay? And this one as well with this. Okay, so I just replaced k minus 1 factorial with this. There's no change. I just don't like this. But by doing this, we can now include k equals 0. Because if we say k equals 0, then the term will be 0, so there's no change in the sum. And now we have some convolution. Okay? This one, we can shift it here. Okay? So we have some kind of convolution here. So what do we do? Let's call this alpha of n. Let's call this beta of k. And let's call this gamma of n minus k. So we have this equality. So I defined alpha of n as this term. I defined beta of n as this term. I define gamma of n as this term. Okay? This one is almost the same, except there's an n here, but I'm defining it differently anyway. So we have this equality. Okay, so recognize the convolution? If we form polynomials on this, let's say the polynomials that we form are called a, b, and c, then we have the polynomial equality a of x equals b of x, c of x. Right? We can easily compute these polynomials, but we're looking for b. So what do? Just divide. We have polynomial division algorithms, right? So let's do that. And now you have b, which contains the answer, which is easy to adjust. It takes n log n time because, as we have seen before, division takes n log n time. That's it. Okay? Faster than the divide and conquer solution, although there's still a large constant behind. So that's not the final problem, because you already know that problem. So this will be the final problem. Okay, so in this problem, you have a weighted undirected graph. Okay, so there are n nodes. The graph is connected and weighted and undirected. And there are n plus 1 edges. So the first step, just compute the minimum spanning tree. No, just all the spanning trees of this graph. Okay? What?
Weight of all of them.
Yeah, compute all the weights of all the spanning trees. Not necessarily the minimum one. And then let's say the weights are W sub 1 and W sub k. Okay, where k is the number of spanning trees. And assume this is sorted, sort the list. So you have to answer queries. Given I, what's the ith value in that sorted list? So that's the problem. There are n nodes up to 10 raised to 5. There are n plus 1 edges. There are not up to 10 raised to 5 queries. Assume the queries are valid. So I is always in this range. Okay? It doesn't go outside. The weights are up to 10 raised to 5.
Can we give a theoretical bound on Q?
What?
Can you give a theoretical bound on Q?
Can we give a theoretical bound on K? Can you? Can you think of one? How many edges does a spanning tree have? N minus 1. How many edges do we have? So can you give a bound?
We just choose.
Yeah, so it's just, so we have an upper bound on the number of edges, or I mean the number of MSTs. It's just n plus 1, choose n minus 1. Right?
Why isn't that the exact
Because not all selections will form a spanning tree. Right? So this is an upper bound. But this is also just n plus 1, choose 2. Which is O of n squared. So there are O of n squared spanning trees.
And the I which you give in a query, it can be less than equal to K or any.
I is less than equal to k. So there's always an answer. What? Wait.
Basically, we find one spanning tree. Now we have two edges only left because the number of edges is n plus 1. So basically, if we want to add the text into the spanning tree, we will have to remove any one edge in the cycle form for that spanning tree.
So you're saying, let's say we have some spanning tree, and there are two more edges.
So if we, this is one weighted spanning tree. Now if I want to add any one edge, I would have to remove any one of those edges which is formed in that cycle. So that can be max n and this can be max.
In these two cycles, you can select n squared.
Multiply this so fast.
Right?
So if the cycles that are there in the graph are disconnected, then like suppose there are some edges E1, E2, E3, and the weights corresponding to them are W1, W2, W3. And here E4, E5, E6, and the weights are W4, anything. So we can make a polynomial which is x to the power W2 and x to the power W3. We can multiply this by x to the power W4, 6 to the power W5, 6 and the resultant polynomials we will get 30. will have the powers as the sum of these weights. So like we have to find the weight of the spanning tree. Only two edges will be removed from this graph, so we can like what would the power of this will be? We will subtract this by 2 summation of weights minus this. So like for that case I am able to go, but when the cycles are connected with that.
Okay, at least that's correct. So let's discuss that. Okay. Okay, so he's right. He's got a partial solution to the problem. So he gave a solution for the case when the edges are disconnected or the cycles are disconnected. Okay, it's possible that the cycle when you add, of course, when you add two edges, then there's at least two cycles in your graph. What happens is you have one cycle and another cycle, and they're not connected. Of course, you can have other nodes coming out of this structure, but you can have. But the thing is, you have two cycles, and to form a spanning tree, you have to remove exactly one cycle, one edge from each cycle. So what do we do then? First, get the weights of the edges in this cycle, sort them. Get the weights in this cycle as well. Let's say you have weights up to Wn or Wm. And let's say the weights here are V1, V2, Vr. What we do is form polynomials. Form this polynomial, multiply that with this polynomial. What happens when we multiply these polynomials? You'll get some terms, but what do you get? For each term here, you get multiplied here. So you'll get terms like this. Okay, and this is exactly the weights that you want to remove, right? And the thing about this is the weights are small. So the product will not be very large. The product will be at most twice this bound, right? So the coefficients will then say how much that term appears. Okay? How many times that term appears. And then the coefficients will definitely be in sorted order. But to get the weight of the spanning tree, just get the sum of the weights and then subtract it by the exponent. So to answer queries, just binary search on this, or there's an easy structure to build on this array. Okay? But the question is, what if the cycles are not disconnected?
Something else, let's say y sub 1 and so on.
Okay.
And now construct polynomials separately. So basically, if you can select one edge from the common edges and one from cycle 1, which is not in that common edges, and then one from the common edges and one from the second cycle, and one from both, but not from the common edges.
Okay. So that's correct. A more elegant way, at least for me, is let's say the cycles are not disconnected. So in the general case, it's going to look something like this. Okay? So if you consider these as the cycles, these are the common edges, and it's going to look something like this. Right? There could be other edges somewhere. Ignore them. Now, if you want to remove two edges, you can choose any of these three pairs. You can remove two here, you can remove these two or these two. So you can consider each of these paths as a different set of edges. Let's say the weights are A1, A2 up to AM, B1, B2 up to BR, and C1, C2 up to CS. Okay? To determine the number of ways in which you can remove from this, you just multiply their polynomials, and then these polynomials, and then these polynomials. And then combine those polynomials together. Right?
What are AB's?
Let's say are the weights of the edges in this path. B's are the weights of the edges in this path, and C in this path.
How do you define B? Like which edges?
I mean, these are edges.
So like what is the characteristic of B?
We're looking at the case when the cycles are not disconnected, and I'm saying that it's going to look something like this in the general case. You can find two nodes for which there will be exactly 3 disjoint paths. Okay? And you can do this. You can build 3 polynomials and then multiply them together, right? How many FFT calls does that take? But before answering that question, notice that the product will not have a very large exponent again. So this one can be combined, and then you can use the same structure as before. But the question is, how many FFT calls does that take? Remember, when multiplying 2 polynomials, you have to take the FFT of the 2 polynomials, and then do the pairwise multiplication, and then take an inverse FFT. So all in all, there are 3 calls. In this case, we need to multiply this pair, and then this pair, and then this pair. Of course, in the most naive way, there are 9 calls, but yes.
You can do it with 2 multiplications. Essentially, A plus B.
How many FFT calls then? 6? Okay. So how?
A plus B into B plus C.
So,
That A is a polynomial.
so take the FFT of A, of B and C.
No, I meant A plus B multiplied by B plus C.
Okay. So notice that we're trying to compute this polynomial. Okay? And you're saying we can do that by first doing this, and then something like this. Is that what you're saying?
Not exactly. Let me just try to.
Okay. But this is one such way. So if you look at this, you need to multiply this and you need to multiply this. So that's just 2 multiplications or 6 calls. Can you do better? What? Yes, you can transform every polynomial once, right?
And also we could do it like while computing AX, like F50 of A, then we can store it instead of recomputing it again.
Yeah, that's the point.
That would also be.
Compute FFT of A, B, and C in the first place, so that's 3 calls. Compute the inverse of this, so that's 4 calls now. Now you don't have to compute the FFT of A plus B because you can just pairwise add, right? So you need to multiply and then inverse. So there are 5 calls instead of 6. Can you do better?
We can do it in 4 in the first place only. Like each multiplication already takes 2 FFT calls. Like instead of going for 2 FFT calls, one for A and B separately, we can make a complex pair and then take that.
I don't like complex numbers, let's say. That doesn't count in some sense because if you take a complex number, multiplying 2 complex numbers is the same as multiplying 4 real numbers. And in the same sense, you're kind of like doing just doing the FFTs in parallel.
Yes.
So I don't want those tricks, let's say. Of course, the very simple thing, you can do it in 4. Take the FFT of A, B, and C, compute this, and then compute a single inverse in the end. That's it. Okay? Remember that you can basically do any operation when you have transformed everything in FFT, right? You don't have to do this first and then do this first. Okay, so you can do it in 4. Even if I add 5 here, you can still do it in 4. Okay? And that's actually, let's say you have to multiply, to raise a polynomial raised to n. What you can do is compute the FFT of A, raise each number to n, and then take the inverse. Okay? Although, of course, it only works if you want a certain kind of FFT, because the degree will be very large. Okay? But in some cases, you don't actually need the product. You don't need this. Sometimes you just need something like this. If you have something like this, that might work. Okay? So I guess that's it. Any questions? Do you have any questions?
In the last one,
Yeah.
we generally do it by repeated squaring, so that takes n log squaring.
Yes. The,
So will your method take n log n?
so let's say we're doing this, and we're taking this power mod this polynomial. Okay. You usually do this by taking the FFT of this, squaring, and then taking the inverse FFT again, and then reducing it mod this, right? And then you have a polynomial of degree less than m. You take the FFT again, and then square, and then take the inverse, and then take the modulo. Okay? Of course, that's going to take m log n, right? Because m log n for multiplication and log n multiplications. But what we can do here is, notice that if you interpret mod in the right way again, what is mod saying? We want this to equal 0. In other words, we want x to the m to equal 1. In other words, we want x to be an mth root of unity. So essentially, we're just computing a of x on nth roots of unity, and that's just FFT of size m, right? And now what we want to compute is a of x raised to n, evaluated at those roots of unity. So what we can do is take the FFT of a of size exactly m, no padding, raise the values to n, and then take a single inverse in the end. That's faster. Of course, the catch is it has to be of size exactly m.
That loosely n.
Yeah, you can use the algorithm, the JK thing that we did, to turn that into an actual FFT. Okay? So that's it. Any questions? Any solutions to the past problems? That doesn't require factorials, powers, binomial coefficients. I don't know. Let's try to discuss the solution of that problem. So you have a grid. There are n columns, m rows. You have to fix r rows. You have to fix c columns. And let's say c is less than or equal to r. If this is the case, then you have to flip exactly one row, one cell for each bad row. But for each bad column, you may flip more than one. But for each bad row, there has to be an odd number. And for each good row, there should be an even number. Okay? So what can we do? Let's define some dynamic programming solution. Let's say f of RC. This says we have to fix exactly r rows and exactly c columns. And we have the assumption that r is greater than or equal to c. Okay? This clear? If this is the case, remember that we have to flip exactly one at each row, at each bad row. Okay? First, let's say there are bad rows and c bad columns. If r equals 0, then there are no bad rows. But since this is true, then there are no bad columns as well. So there's one way to do that, which is to flip nothing, right? Now, what if r is greater than 0? We have to flip exactly 1 at each bad row. Let's look at one particular bad row and determine where we want to flip. We can either flip at a good column or a bad column. If we flip up at a good column, or a bad column, for example, what happens? Then there will be r minus 1 bad rows and r minus 1 bad columns. R minus 1, C minus 1. But we still have to select which bad column we want to flip. So there are C choices for that. Okay? On the other hand, we can also flip a bad column or a good column. And how many? When doing that, we increase the number of bad columns by 1. So the recursive call will just be this. And how many choices are there? N minus C. That's it. No powers, no factorials. No, this is it. Of course, this only applies if r is less than C. Okay? If
R is greater than C.
If r is greater than C. If r is equal to C, then you only have this choice, right? You cannot flip a good column this way because by flipping, you'll get a more bad columns.
We need r greater than c plus 1.
What?
To apply that, we need r greater than c plus 1.
A what?
We need r greater than c plus 1 to apply f r minus 1 c plus 1.
This one, yes. But remember that R and C have the same parity, so that will be fine.
Don't we need to prove an invariant which decreases, like to prove that a DP state has already been examined?
In this case, we're only examining all flippings where we flip exactly one cell from each bad row. And we can show that we're checking each of those exactly once because we're only checking each row one by one, right?
But how can you say that you have already computed value of f of r minus 1 comma c plus 1?
How? What do you say? What do you mean I've already computed? This is dynamic programming, so you start from small r first.
So like we run this algorithm on two loops. So R is the outer loop, C is the inner loop.
Yeah.
Whenever R minus 1 is traversed, the whole C will be traversed, right?
Okay? Is this clear? You don't need exponential generating functions. You don't need FFT.
Isn't there any way to compute this directly
What do you mean directly?
without using GP?
You can do brute force, but it's going to be exponential.
Some formula kind of stuff for
Try deriving one. You can try. Okay? Is it clear why this avoids double counting? We're only considering each bad row one at a time and in a very particular order. Okay? And at each step, there are only really two choices. Flip a good column or flip a bad column. So we only have to remember how many good columns we currently have. Okay? That's it. That's it. Any questions? Feel free to ask if you have questions. But the session's over.